Good evening, everybody, and welcome to another organic chemistry review session. In today's session, we are going to discuss the chemistry of Enolate Anions, and more specifically, we shall discuss the chemistry of Malonic Ester Synthesis and Acetoacetic Ester Synthesis. Before we start the session, let me go ahead and acknowledge some of you who have already joined us. I see a lot of you are here already. Area Wale, Dom Payne, Eli Rono, Elisha Mackenzie, Ines Kifando, Janelle Radire, Jaconda Kepas, Makamba Saki, Natalia Stepanova, Shine Aline, and I believe that's about all of you who have joined us so far. You are all welcome. Okay, to get the session started, I am going to call on Ariel. Can you go ahead and read this question for us?
List the steps in the preparation of the following compound.
Okay, very good. And thank you. Okay, so what they want you to do here, they have given you this compound here. Okay, and they want you to give the synthetic scheme for this compound. Let me ask you this. What class of compound is this? What class of compound is this? Okay, carboxylic acid. Okay, very good, very good, very good. Okay, that is correct. Now, they've also given us a couple of starting material. And here, starting material 1 and starting material 2. So another question that I have for you, what is the name of this starting material here, number 1? Okay, this right. Okay, Malonic Ester. Excellent. Very good, very good. Malonic Ester. I see somebody asked a question for me. Let me see here. Okay, Janelle, go ahead and ask your question. Okay, okay. Somebody say ethyl malonate. That is also correct. Okay, that is the question they are asking you. They want you to determine what starting material to use here. Okay, so we are going to get to that. I think that is the question that Janelle is asking. How do we know which starting material to use? But we are going to get to that question shortly. Now, what is the name of starting material number 2? What is the name of starting material number 2? Okay, right here. Ethyl acetoacetic ester. Okay, very good. That is also correct. Ethyl acetoacetic. Okay, in other words, this is acetoacetic ester. So you are given 2 starting material, the malonic ester and the acetoacetic ester. Now the question is, you need to determine which one of these are you going to use to make this compound here. Let me ask you that question. Which one of these are you going to use? Are you going to use 1 or 2? Okay, excellent, excellent. Okay, you guys say 2, which is ethyl acetoacetate, which is the acetoacetic ester right here. So that is correct. Now, how do you know that? Oh, by the way, I'm sorry about that. Let me take that back. That is not correct. That is not correct, okay? Okay, that is not, you guys say acetoacetic ester. Okay, but let me ask you this other question. For those of you who say acetoacetic ester, why did you pick acetoacetic ester? Why did you say it is this here? Any reason why? Keep in mind what we are making here. We are making a carboxylic acid because of the carboxylic acid. Okay. Now keep in mind, if you are going to make a carboxylic acid directly from any one of these, only the malonic ester will give you a carboxylic acid. Therefore, the choice of starting material has got to be number 1, because with the acetoacetic ester, you will be getting a methyl ketone. Okay. I see Ines is saying after the acetoacetic ester, you use iodoform reaction. Now, this question is asking you how to make this direct synthesis of this molecule from each one of these here. Okay. So anyway, let us go to my notebook so we can finish this question. Okay, so this is the structure here. Janelle, now coming back to the question you asked earlier, I hope I have answered part of the question that you asked earlier in terms of how do we know that we need to use malonic ester. For example, here we know that we have a carboxyl. We are supposed to make this carboxylic acid directly from malonic ester. In other words, we are going from here. This is our malonic ester here. Okay, anytime you are told to make a carboxylic acid directly from either malonic ester or acetoacetic ester, you know that the correct choice of starting material must be the malonic ester, because it is only malonic ester that will give you a direct synthesis of carboxylic acid. So therefore, we need to do this here. Go from here to here. Okay, so we have CH2, and then we have this. Okay, so we need to go from here to here, and to do that, let us see what do we do. If you take a look at this here, if you take a look at the malonic ester, these carbons here, okay, will be this carbon in the product, because we have to expect that this carboxy group will have to be one of these carboxy right here, okay? Because one of these will be gone, okay? So therefore, if that is the case, well, how do we make this compound? Let me now say, what is the starting material we are going to use? What will be the first step we need to do here? Can anybody give me what is the, okay, etoxide, very good. Okay, you guys have given us etoxide to use. So we do the etoxide. Then after you do the etoxide, you are going to form the enolate anion. Then once you form the enolate anion, then you need to use an alkylating agent. So what will be the alkylating agent? Let me number this carbon for you. Okay, let us look at this here. Carbon 1, carbon 2, 3, 4, 5, and 6. Okay. Now, your alkylating agent, the leaving group must be attached to each one, any one of these carbon here. Can you let me know which of these carbon here, the leaving group you are going to use, will be attached to? Which one of these carbon? Okay, 1. In other words, excellent, that is correct. In other words, what you are saying here, we are going to use this alkylating agent to okay, this time let us use a bromine atom as the leaving group. It's a leaving group. Okay, so now once we do that, then we get this here. I'm sorry, I don't want to confuse you guys here. This should be from here. This is here. Okay, because this is the product right here. Okay, so now we have this. Okay, we have that. Okay, we have that. So now what is the next step? Are we going to, what would be the next step right here? Once we do the alkylation right here. Okay, hydrolysis. Very good. We are now going to do our hydrolysis. To the hydrolysis, and the hydrolysis now will convert the ester functionality right here to carboxyl group. Okay, so now we have this. Let me get this out of the way. Okay, so now this is hydrogen here. Okay, now we form our carboxyl group. At this point, what will be the next step? Heat. Very good. Now we apply heat. We apply heat, now we get this here. Now we get that product, and that is this product right here. That is this product right here. Okay, so what have we done? What we've done here is what we refer to as the Malonic Ester Synthesis. Okay, the sequence of reaction, Malonic Ester Synthesis. Okay, which is the sequence of reaction starting from ethyl malonate or malonic ester, and then you form the enolate anion by reacting with the toxide. The enolate anion will then will be alkylated using an appropriate alkylating agent. Now the point here with this alkylating agent is that this is an SN2 reaction. This is an SN2 reaction, which is to say that this alkylating agent here, the leaving group must be attached to either a primary carbon or a secondary carbon. Okay, each one of these will be sp3, hybridized carbon, primary carbon, or secondary carbon. That is very, very important. Okay, so now once you do your alkylation, then you do acid catalyzed hydrolysis to transform the diester to diacid right here. And then once you form the dicarboxylic acid, then you apply heat. When you apply heat, you are going to lose a carbon dioxide right here. So carbon dioxide will be lost. So here we form carbon dioxide. And then you also notice here, this hydrogen here is actually one of these hydrogen here, right here, belongs to this hydrogen here. So what this tells us is that at the end of the Malonic Ester Synthesis, oh, I'm sorry, not that one, this one here. This hydrogen here. So what that tells us is that at the end of the Malonic Ester Synthesis, you must have an hydrogen and alpha hydrogen. In other words, the alpha carbon, that is the carbon that is attached to the carboxyl group, must always contain an hydrogen atom. Okay? Now, what do I mean by all of this? Let me ask you a couple of questions. Supposing, therefore, based on what I've just told you now, supposing I ask you, based on what I've just told you, supposing I ask you, can you make this compound here directly from Malonic Ester Synthesis or Acetoacetic Ester Synthesis? Yes or no? No. Okay, why? That is correct, why? That is correct, why? No hydrogen on the alpha carbon. Excellent. Keep in mind, notice here, you cannot make this compound directly from Malonic Ester Synthesis or Acetoacetic Ester Synthesis, because this alpha carbon here, this carbon that is attached to the carboxyl group, does not contain an hydrogen atom. Okay, the only way you know that is because you know the mechanism of the Malonic Ester Synthesis. Okay, now, let me also ask you another question. Supposing I give you this. Can you make this compound directly from Malonic Ester Synthesis or Acetoacetic Ester Synthesis? Yes or no? Okay. Okay, I see a lot of yeses here. The answer is no. The answer is no. Okay, for those of you who said no, why no? Why no? No is correct. The answer here is no. No, why no? Okay. Wouldn't follow exactly. Excellent. Lorenzo, that is correct. Lorenzo has just given us the answer because look at this here. Remember in the Malonic Ester Synthesis or the Acetoacetic Ester Synthesis, okay, let us go back to this. Okay. Remember the first thing we do? We form the Enolate Anion, right? And then what do we tell you that we do after that? What do we tell you that we do after that? We do alkylation, right? Okay, we do alkylation. And what do we tell you about the alkylation? What do we tell you about the alkylation? The alkylation must be SN2 reaction, okay? So therefore, if you look at this molecule here, okay, if this molecule here, this carbon here, is this carbon, okay, so therefore, if you want to generate your enolate anion here, then what you are assuming here is you need, as an alkylating agent, you have to use this as an alkylating agent right here. You cannot do this. This is a tertiary substrate. The leaving group is attached to a tertiary carbon. You cannot have an SN2 reaction on an tertiary carbon. So keep that in mind. And that is why we keep telling you that in this process of alkylation, it is an SN2 reaction. So in this particular instance, we cannot obtain this molecule directly from malonic ester synthesis or acetoacetic ester synthesis. Okay, that is the why. The why is because in this case we cannot do an SN2 reaction involving a tertiary substrate. So that is the why. Okay, now let us go back to. Is there any question on this? Okay, well, I tell you what, while we are on this topic, let me ask you one more on this. Supposing I have this. Supposing I have this here. Because this is very important. Supposing I have this. Can you make this compound directly from acetoacetic ester synthesis or malonic ester synthesis? Yes or no? Yes or no? Okay. Okay. No is correct. Can anybody tell me why no is correct? Yes, no is correct. Why? Okay, just a minute. Let me number the carbon. Let me number the carbon. This is carbon 1, carbon 2, carbon 3, carbon 4, 5, 6. Let us say this is carbon 7. Okay? Why do you say that we cannot make this directly from acetoacetic ester or malonic ester? SN2 reaction not possible. Excellent. SN2 reaction is not possible on an sp2 carbon. This is an sp2 carbon right here. That is an sp2 carbon, and you do not do an SN2 reaction on an sp2 carbon. You only do a SN2 reaction on sp3 carbon, and that carbon must also be primary or secondary carbon. Please keep that in mind, very important. Okay, any question on this before we go further? Okay, good. So now, going back to this question here, the question they asked us the question they asked us was what would be the alkylating agent. In this case, this is the alkylating agent right here. Okay? Okay, so let us go to question number 2. Okay. Natalia, go ahead and read this question for us.
Identify all the acidic hydrogens pKa less than 25 in the following substances.
Okay, thank you, and very good. Okay, so in this case, all they are simply testing your knowledge of is whether you know which are the acidic hydrogen, generally the pKa less than 25. Okay, so let us take a look at, let us say this is molecule A. Let us take a look at molecule A. Which of the hydrogen here will be acidic in molecule? Just give me the letter. In molecule A, which of the, okay, C. Okay, very good. Only C will be, that is correct. Only C will be acidic. Can anybody tell us why only C will be acidic? Anybody? Why? Yes, C is correct, but do you know why? Why? Okay, because, no, not because it is attached to oxygen. It isn't attached to oxygen. Okay, try some more. Why is this acidic and these other hydrogens are not acidic? Okay, now what do we get? It's alpha to the acidic. Okay, we know it is alpha to the acid chloride. And so what makes it acidic, therefore? What is it that makes it acidic? Okay, keep in mind, whenever you say an hydrogen is acidic in an organic molecule, what you are actually saying is the conjugate base is stable. That is what you are saying. You are referring to the stability of the conjugate base. In this case, the conjugate base will be this here. Okay, once you remove the proton from here, you have the enolate anion, which is your conjugate base, and that enolate anion can be stabilized by resonance. And that is why that hydrogen is acidic, because of the stability of the conjugate base. Okay, this conjugate base is stabilized by resonance. Keep that in mind. So anytime we say this, a particular hydrogen is acidic, what compared to another set of hydrogens, in essence, what we are saying is the conjugate base of that hydrogen is much more stable than the conjugate base of the other set of hydrogen. So if you remove hydrogen from here, the conjugate base cannot be stabilized by resonance. Okay, so that is the answer here is C. Now let us go to molecule B. Molecule B, let's take this out. For molecule B, which is the acidic hydrogen here? For molecule B, right here, which will be the acidic hydrogen? For molecule B, just give me the letters, the acidic hydrogen. Okay, D, excellent. That is correct. D is correct, yes. And why? Why D? Why D? Why D? Why D? Why? Okay, same reason as above, excellent. In other words, the conjugate base of this here, in other words, the conjugate base of this, once you remove the hydrogen, this conjugate base will be stabilized by resonance. Okay, Natalia said the same reason as above, that is correct. So therefore you have this, you have this, so you have this here, and then you have this. Okay, this should be fairly easy. Okay, Jaconda, read this question for us.
Draw the organic product or products of the following reaction.
Okay, thank you, and very good. Okay, so now draw the products of the draw the product of the following reaction. Okay, we are using LDA, and then we have cyclohexanone. So let me go ahead and label this carbon here. 1, 2, 3, 4, 5, and 6. Okay, now let me also now label this here. Let us say this carbon here is 7. This carbon is 8. This carbon is 9. Okay? Okay, so what will be the product here? Just give me the numbers, the carbon that are attached to each other. If 2 and 9 are joined together, give me 2 and 9. If 3 and 8 are joined together, give me 3 and 8, so I could write the product. What will be the answer here? Okay, 2 and 9. Somebody said 2 and 9. So you are saying this 2 is joined to 9. No, that cannot be correct. Okay. Okay. 2 and 6. No, that cannot be correct. Okay. 2 and 7. Excellent. 2 and 7. Okay, keep in mind that is correct. 2 and 7 is correct. Okay, because what happens here, the LDA, which is this here, what does it do? It forms the enolate anion. Actually, it could be 6 and 7. Did somebody say 6 and 7? Yes, or 6 and 7. That is correct. 2 and 7 or 6 and 7. Okay, so LDA, what does it do? It forms this enolate anion here. Once you form the enolate anion, then the alkylating agent comes in, which is this here. Okay, you see here, the iodine, which is a good leaving group, is attached to a primary carbon, which is sp3 carbon, right here. Okay, so then what happens? The enolate comes in, acting as a nucleophile, attack this carbon here, and this will leave. So therefore, you get this product. So the answer could be attachment of 2 and 6. I'm sorry, 2 and 7 or 6 and 7, which is here. Okay, so that should be fairly simple. Everybody should be able to get that right. In this case, nobody is asking you for the mechanism. The reason I am showing the mechanism here, so that is simply just to further illustrate to you exactly what is happening. You could very well have just done this based on the question they ask here. You could simply just write the product. Just do this. That would be just fine. Okay? Okay, so let's go to the next one. Okay, let me see here. Let's make this a little smaller. Okay, Elisha, can you go ahead and read this question for us?
Draw the alkyl bromide used in the Malonic Ester Synthesis of ethyl 2-methyl-4-pentanoate.
Okay, thank you, very good. Okay, once again, this is a case of Malonic Ester Synthesis. What they want us to do is simply give the alkyl bromide that is needed. But what I want us to do here is to give the complete synthetic scheme, okay? Before you do that, we need to know what the structure of ethyl 2-methyl-4-pentanoate is, okay? So therefore, they want us to do this. Start with ethyl malonate or malonic ester. Okay, so we start with that. And then they want us to make this compound here. ethyl. It is an ester. Ethyl 2-methyl pentanoate 2-methyl. Methyl group is in the 2 position, and then say 4-pentanoate. In other words, you have a double bond in the 4 position. Okay, so that is carbon 1, 2, 3, 4, 5. So they want us to go from the malonic ester to this molecule here, ethyl 2-methyl 4-pentanoate. Okay, so what I want us to do, let us go step by step. So I want you guys to give me all of the steps that I need. Okay, what is the first thing that I have to do here? What is the first thing that I need to do? Okay, ethoxide, very good. Okay, and what does that give me? What does it give me? What does it give me? Enolate. Okay, very good. So let us, folks, I am doing this for the benefit of those of you who may not be too comfortable with this synthesis yet, but you do not have to give the mechanism unless I ask you to give the mechanism. So now you form the enolate anion. So once you form the enolate anion, then what do we do? Let us take a look at the problem here. Let us do some analysis. Okay, this here, this carbon here, okay, will have to be this here, because that is the carbon that is alpha to the carboxyl group, the carbonyl group. Okay, so this carbon is this carbon, okay? Okay, therefore. So, if you then take, yes, go ahead, Elisha, go ahead. Ask your question. Okay, let me see what your question is. Are you going to have to do 2 alkylations because of the extra? Yes, yes, that is correct. You have to do 2 alkylations. That is correct. So the question that Elisha is asking in this particular question, do we need to do 2 alkylations? That is correct. You need to do 2 alkylations. So the first part is this here. This will be a source of alkylating agent. Okay. And then this here will be the source of another alkylating agent. So those are the 2 alkyl groups that you will need. And that is the question they are asking here. Okay? Okay, but let us go ahead and give the process. Okay, so now we have identified the alkylating agent. So what do I do here? I could do the methyl iodide. Okay, I do methyl iodide, and then that gives me, let me use a different color here. Use a green color. Okay, so I have this. And then the methyl group has attached itself to here. And then I do another alkylation. Once again. Ethoxide again. Which now means that I will get another enolate anion. Okay, now we have this methyl is here. Now the Enolate anion is here because we removed this proton here. Okay, so now at this point we are now going to introduce this other alkylating agent right here. Let us use another green. To use the this will be an allyl bromide. This is called allyl bromide. Okay. So now once we do that, we now get our product. Okay. If you see that, give me a happy face. Oh, I'm sorry. No, we don't have our product here. I'm sorry. Take that back. Because what this gives us, we see I have the ester here. We need to lose carbon dioxide. I'm sorry, I was trying to jump the gun. Okay, so not yet to the product yet. So we now have this. Let me make this a little shorter. So I give myself some room. Okay, so now we have this. Now we have the two alkyl group attached to this. Okay, so now at this point, now what will be the next step at this point? What is the next step at this point? Oh, okay, very good. Now we do the hydrolysis. Okay, we could combine the hydrolysis and the heat together. So we say heat. Okay, so this becomes carboxyl group. This becomes carboxyl group, and one of these will lose carbon dioxide, and then of course the hydrogen on the carboxyl group will come right here. So therefore we are going to get this here. So we get this. So now say we have this here. Okay. One of those hydrogen will be here. And then the other one will be the green alkyl group. Okay. Now, once we get that, then what is the last step? Anybody know what the last step is? What will be our last step? Because at this point we have a carboxylic acid. Keep in mind we need an ester. The product required for us to make an ester. Okay, so what do we need at this point? We have this here. So far, this is what we have. This is a carboxylic acid. But we do need an ester. So what is the next step or the last step? What will be the last step here? Anybody has an idea? So far, this is where we are. We have made this. Okay, Fischer esterification. Exactly, Fischer esterification. So they are excellent. So therefore, at this point, we will take this, react with ethyl alcohol, because they want us to make an ethyl ester in the presence of acid. Okay? And therefore, so what have we done? We have finally got into this product right here. So let me make this easy for you. Let me go to Let me go to a blank page. Okay, so without going through the mechanism, you could very well do this in an exam. What we did now, you could just do this. You could say, step 1, ethoxide. Okay, step 2, iodide. Step 3, another ethoxide. Okay, step 4, another alkylating agent. Okay, and then step 5, you could then do step 5. At that point, you want to do the hydrolysis and heat. Okay, and then you could say step 6. Now, if you do this, you make sure you know what you are doing. Because if you do this and any one of these steps is wrong, I will not give you credit. Okay, but the advantage of going through this step by step is that at least I will give you partial credit if you are wrong along the way. But if you know what you are doing, you could do this. Okay? You could do this. So let me walk you through this. Okay? Step 1. What does step 1 do? Can anybody tell us? Just write for me. What does it do? Step 1. What does it do? Okay, enolate anion. Very good. What about step 2? What does it do? Step 2, what does it do? Alkylation. In this case, okay, alkylation. Okay, about step 3, enolate anion again. Okay, about step 4, alkylation. Very good. About step 5, step 5, there are 2 processes going on here. What is step 5? Okay, whenever you are not sure, make sure you write it out. Write it out so that we know exactly what the product is. But you guys should be able to tell me what step 5 is. Okay, that will be hydrolysis and the decarboxylation. Okay, this is hydrolysis / decarboxylation. Okay, and finally step 6. What is step 6? Fischer esterification. Very good. Now you could do this if you know what you are doing. But I would then advise, if you know what you are doing, write out what I've just done here. Say at this step, this is what you get, this is what you get, this is what you get. Okay? Then I will give you your credit. Okay, let us go to the next one. Where were we? Okay, we've done that already. We've done that already. Okay, let us see here. If your mic is working and I have not spoken to you tonight, can you read this question for us?
Specify whether the ketones below can be prepared by an acetoacetic ester synthesis.
Okay, very good. That's Ariel Mangum. Very good. Thank you. Okay, so what they want us to do here is to specify whether the ketones below can be prepared by an acetoacetic ester synthesis. In other words, this is direct synthesis. That is what they mean here, direct synthesis, not not after the synthesis, then you do something else. Okay. Okay, can you make this by directly from acetoacetic ester synthesis? Yes or no? Okay, let me label this compound A and compound B. Can you make compound A by direct acetoacetic ester synthesis? Yes or no? Yes or no? Okay, yes or no? Keeping in mind that this will be the alpha carbon of the acetoacetic ester. You say yes? Okay, how many people say yes? No, that is not correct. Take a look at this. Take a look at it. Does this halogen here, if you look at this here, if you have to, can you guys hear me? If you can hear me, give me a happy face. Okay, I just lost my my internet, so just give me 1 second, okay? Okay, folks, just give me 1 second. I'm going to log out, and then I'll come right back in, okay? So stay right where you are. Okay, can you guys hear me? Okay, very good. Okay. Okay, this is where we are. Okay, the question that I asked you was, can we make this using acetoacetic ester synthesis? The answer here is no. And why is it no? The answer is no. If you look at this here, look at the acetoacetic ester. Okay, that is the acetoacetic ester. This carbon here is this carbon, okay? Now, in order for us to make this compound, okay, the alkyl group that we need will have to be a tertiary alkyl group, okay? And we cannot do that. Why? Does anybody know why that will not work? Anybody know? Oh, okay, let me see here. Does not go exactly because a tertiary carbon will not undergo an SN2 reaction. So that is why this is no right here. How about B? About B? Okay, will B work? Yes, yes. B will work because we have an hydrogen here. Because we know we have an hydrogen here. Okay, we also know that if we have to make this, we need, okay, let me ask you this. How many alkylation would you need to make this? How many alkylation? 2, exactly. The 2 alkylating agent will have to be this here. Okay, and you use 2 of these, and this carbon here is an sp3 carbon atom that is a primary carbon. So you could do an SN2 reaction here. So the answer here is yes. Okay? Let's go to the, it's okay, it's almost 9 o'clock. Let's do one more question. Okay, Somebody go ahead and read this for us if you have not spoken to us already.
Indicate whether the compounds below undergo the haloform reaction.
Okay, thank you. Very good. And that is Kiera Bradley. Very good. Okay, so now what they want us to do here, to indicate whether the compounds below undergo the haloform reaction. When we say haloform reaction, we mean either iodoform reaction or chloroform reaction or bromoform reaction. All of these reactions here, each one of these, what they do, they all react with a methyl ketone to give carboxylate, and then when you add acid to it, of course, then you get your carboxylic acid. The point here is the haloform reaction. What it does is to convert a methyl ketone to a carboxylic acid. Once you add the dilute acid at the second stage. Okay, the same thing will happen here. Of course, here you form sorry about that. Here you form the iodoform right here. You form iodoform. Okay, here you form chloroform, and here you form bromoform. Okay? Okay, now, which one of these will undergo the haloform reaction? Okay, let us label this A, B, and C. Which one? The tunnel. C, exactly. This is correct. That is correct. This will undergo. This is the only methyl ketone we have in this here. So this is yes. Okay, this is no, and this is no. Okay? That's a fairly simple one. Okay, okay, we will do this in class tomorrow. By the way, this particular molecule here is called barbital. It's one of those pharmaceutical drugs. If you take a look at this here, while you go home tonight, before we get to class tomorrow, while you go home tonight, this molecule here, we could synthesize this molecule using the malonic. Okay, they've already told us using the malonic ester. Okay, we could do that. Then once you use the malonic ester to form part of this molecule, then you could then react with this here. This is urea. So what this question does is to combine what we learned in chapter 21 and what we are doing in chapter 22 right now. Okay? So this part of the molecule comes from the malonic ester synthesis, and the upper part of the molecule, this here, come from the nucleophilic acyl substitution of the product from the malonic ester synthesis of the malonic ester product. So what I want you to do when you go, before you come to class tomorrow, see if you can work out the mechanism of this reaction. Okay, starting from malonic ester. It's a very simple process. You use malonic ester. Then once you get the malonic ester product, then you react with this here, keeping in mind that you have non-bonding pair of electrons here to get your final product right here. So see if you can do that tomorrow, and then when we come to class tomorrow, we will do this together. Okay, so let's go to the next one. Okay, let's see here. I think we've done something. No, okay, let's just move. Okay, there's one more question I want us to do before we leave. Where is it? Where is it? No, okay. This here. I want us to do this together. And I will need your help to do this. Okay? Can somebody just read this question for us? We do this, then we go home. Just anybody can read this for us.
The Favorskii reaction involves treatment of an alpha haloketone with base to yield a ring-contracted product.
Okay, thank you. Very good. Okay, so what they have here, the Favorskii reaction involves treatment of an alpha haloketone. This is an alpha haloketone. In other words, you have an halogen attached to the alpha carbon here, and this is a ketone with base to yield a ring contracted product. Okay, I'm going to give you some guideline, and then after that you will then guide me through how do we go from here to here. What I want you to use here, use all of your knowledge that we've gathered from chapters 21 and 22 to solve this problem. Okay, the first thing I want you to know is we are going to use this as the base. Somebody say we need two numbers. Yes, yes, very good. Okay, yeah, I'm going to number the carbon for you. Okay, let us start here. We are going to start with an hydroxide. And then once we do that, we're going to do this. Enolate ion formation. Okay? Then 2. Once we form enolate ion, then we are going to do an intramolecular SN2 reaction. Okay, let me write this here, formation. Okay? Then 3. Then we are going to get a nucleophilic, something that is similar to nucleophilic acyl substitution. So in other words, we are combining all of those things that we've done in chapter 21 and 22 here. Nucleophilic acid substitution. Okay, and finally, to get to this product here, we are going to do protonation. I would say acid-base reaction. Okay, or I might call this protonation. Okay, okay. Before we proceed, let me go ahead and number this carbon. This is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, carbon 7. Okay? Okay, so let us start. Okay, the first step, anybody tell me, where are we going to form the enolate ion? Just give me the number. Okay, we are going to form enolate ion. Where? Okay, no, 7 is not right. Because look at 2. Look at 2. Look at step 2. Exactly. Look at step 2. Because if you look at step 2, that will give you a guide as to what step 1 should be. So somebody said you form the enolate ion here. That is correct. You form the enolate ion on carbon number 2. So I want you guys to guide me through this. So we form enolate ion here. Bromine is here. Okay, now step 2. What is going to happen in step 2? This here. So far we've done this. About step 2. What is going to happen? I say intramolecular SN2 reaction. What do you think is happening? What do you think is happening? Okay, 2 attach 7. Excellent. 2 attach 7. That is what we mean by intramolecular, because the nucleophile and the leaving group are in the same molecule. Okay, so this carbon attacks this. Okay, and when that happens, this goes. So that is an intramolecular SN2. Okay, so what do we have here? So we have this. We follow this very carefully now. So we form a cyclic 3-membered ketone. Okay, the bromide is gone. Okay, now about step 3. What do you think is going to happen in step 3? By the way, this is here. We form water here. Okay, what do you think is going to happen in step 3? Nucleophilic acyl substitution. Keep in mind, this is where we want to go. OH attached carbon 1. Excellent, excellent. Hydroxide attached carbon 1. Okay, that is exact. That is true. So now, attached carbon 1. And when it does that, this pi electron goes to oxygen. Okay, now we form this here. Okay, this is still here. Okay, now, this is an alkoxide. Now, what is going to happen now? What is going to happen now? Let me erase. We've done these 3 steps. We've done this. We've done this. Okay, so let me take it out of the way. So I make myself some room. Okay, what is going to happen now? Okay, carbonyl forms and 1 and 7 breaks. Excellent. Let me number the carbons again. This is carbon 1. This is carbon 2. This is carbon 3. This is carbon 4. Carbon 5. Carbon 6. Carbon 7. Okay, so somebody say carbonyl will reform. We are going to reform the carbonyl. That comes right back here. And when you do that, okay, this will break. The bond between carbon 1 and carbon 7 will break, and thereby place the electron on here. So therefore, that gives us this. So that gives us this. Okay, so I now say I have this here. this here, this here. Let us number the carbons. This is our carbon number 1, carbon number 2, okay, carbon number 3, carbon number 4, carbon number 5, carbon number 6, and carbon number 7. And now what happens now? So therefore, this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, 6, and 7. So now what happens next? The last step, we need to do the last step. What happens here? Yes. Praveen, yes, you are correct. The bonds that could be broken could also be between carbon 1 and 2. That is also correct. We could also break carbon 1 and 2. That will give also the same product. Yes, you are right. Okay. So at this point, the last step here is protonation, in which we have this here will come in, this anion here will come in and grab a proton from here, and then we are going to regenerate the hydroxide. We form this, plus we form the hydroxide. And that is how we get to this compound here. Now, this is what we call the Favorskii reaction. This reaction is so common and it is so simple, and also it is very predictable that we could actually, supposing I do this, if I give you this, anytime you have an alpha halo ketone, cyclic ketone, let us say we have chlorine here, and if I do this hydroxide, and I say, what is the product? What is the product? Okay, what is the product? Okay, what do you think the product will be? If I give you this here, okay, cyclopentane carboxylic acid, excellent. It is such a predictable reaction that we could actually use this Favorskii reaction as a synthetic method to make carboxylic acid, cyclic carboxylic acid. Okay? Okay, what this does, it gives you ring contraction. In other words, if you have a 6-member ring, you end up with a 5-member ring. If you have a 7-member ring to start with, you end up with a 6-member ring. Okay, now for example, supposing you have a 5-member ring, this is not very common, but it could also happen. Supposing you have this, and I do this. I say, what is the product? What will be the product? What will be the product of this reaction here? Okay, what will be the product? We have, okay, cyclobutane carboxylic acid, exactly. Very good, excellent. Cyclobutane, I'm sorry, let me write that better. So this will give you cyclobutane carboxylic acid. So the Favorskii reaction is an excellent reaction for the synthesis of cyclic carboxylic acid using what we call ring contraction. In other words, if you start with a cyclic ketone with an alpha halogenated carbon, then you could react with hydroxide to form a cyclic carboxylic acid. So I think we have come to the end of our session today. The time is well over 9 o'clock. Is there any question before we leave? Okay, if there are no questions, I am going to stay behind for another 5 minutes for those of you who may have some questions for me. And then for the rest of you, enjoy the rest of your evening, and I will see you tomorrow.